Now that we have reviewed the algebraic relationship between a function and its inverse, we're free to examine the relationship between the derivative of a function and the derivative of its inverse. We'll begin by finding the derivative of an inverse function. Let's begin with a presupposition. If f of x is continuous, and by the way, sometimes you'll see me abbreviate continuous with a C followed by an arrow. If f of x is continuous on its domain, then f inverse of x is also continuous on its domain. Now, why is this important? We need to recall from Calculus 1 that continuity implies differentiability. So if a function is continuous, then its inverse function is also continuous and therefore differentiable. Now, the following theorem will express the relationship between the derivative of a function and the derivative of its inverse. Suppose that f and g are inverse functions. Then g prime of x is equal to 1 over f prime of g of x. Notice we've got a composition there in the denominator. Now, to help you understand this formula, we're going to go through the proof. First of all, we're beginning with the supposition that f and g are inverse functions. So we can say, since f and g are inverse functions, that is, they satisfy all the properties of inverse functions, including the fact that their composition is equal to x, we can say, then f of g of x is equal to x. The composition of two inverse functions always yields the output of x. Now, we're going to take this relationship and we're going to differentiate both sides with respect to x. Notice I'm using that differential operator, d over dx. That tells me differentiate with respect to x. Now, on the left side, we've got the composition of two functions. So to differentiate the composition of two functions, we must apply the chain rule. The chain rule says we're going to differentiate the outside function first while keeping the inside function the same, and then we multiply by the derivative of the inside function. So there's our chain rule applied. On the right side, the derivative of x with respect to x is very simple. We get 1. Now, we can solve for g prime of x by dividing both sides by f prime of g of x. And that is the proof. Now, to clarify this a little bit, notice we started with the assumption that f and g are inverse functions. Let's go ahead and rewrite this formula using inverse function notation. So instead of using g, let's rewrite it as f inverse of x. So where I see the g, I'm going to replace it with f inverse. So on the left side here, I have the derivative of f inverse is equal to, on the right side, we're going to keep f, that's the original function. This is a prime, not an inverse, right? Then I'm going to replace g with f inverse of x. So here's what the formula looks like using inverse function notation. And once again, this expresses the relationship between the derivative of a function and the derivative of its inverse function. Now, we can make this more specific in the next corollary. A corollary is a result derived from a more general theorem. Suppose that f of x naught equals y naught. Now, notice here we have subscripts on the variables. Anytime you have subscripts on the variables, that indicates that you're dealing with constants. And ordinary x and y, those would be ordinary variables. Subscripted variables represent constants. So here we've evaluated our function at a specific input and we've gotten a specific output. Now, if this is true, then f inverse of y naught would be x naught. Notice here we've just reversed the x and y because we're dealing with inverse functions. Thus, f inverse prime of y naught is equal to 1 over f prime of x naught. Now, I want to keep this revised theorem up here because notice this argument is a little different than the information that I have right here. So let's apply an intermediate step here. I'm going to come back up here and I'm going to use this edited formula we have and evaluate f inverse prime of y naught. This is going to be 1 over f prime of f inverse of y naught. So the reason that the denominator here, or the argument of f prime, looks different than the argument that we have here is because we're coming back over here and observing that f inverse of y naught is equal to x naught. So f inverse of y naught simplifies to x naught. So what does all of this mean? This means that we can evaluate the derivative of the inverse function in terms of the derivative of the original function. This formula will be useful if we don't know either the inverse function or its derivative. Let's apply this to an example. Given f of x equals tangent of x, find the slope of its inverse function, inverse tangent or arctangent of x, at ordered pair 1 pi over 4. Now we know that slope is code for the derivative, right? To get the slope of a function, we need to find its derivative. But notice we're trying to find the derivative of inverse tangent of x, and at this point in time, we don't have a formula for the derivative of inverse tangent. Now, I will not disappoint. We will learn that formula very soon. But remember, because of our theorem, we don't have to be able to find the derivative of the inverse function if we know the original function, because there's a relationship between the derivative of the original function and the derivative of the inverse function. Now, it'll be really helpful on this problem if we can identify x naught and y naught. Notice that the given ordered pair belongs to the inverse function. We know that inverse tangent of 1 is equal to pi over 4. So y naught here is 1 and x naught is pi over 4. If I reverse that, okay, let me go ahead and write this down. F inverse of 1 equals pi over 4, so switch it around, f of pi over 4 equals 1. Notice tangent of pi over 4 does in fact equal 1. Now to be very clear, I'm going to write our formula here so we can follow it. We learned that f inverse prime of y naught is equal to 1 over f prime of x naught. Now f inverse is inverse tangent. So I'm finding the derivative of inverse tangent. We have already identified that y naught is equal to 1. This is going to be equal to 1 over f prime, not inverse, that's the derivative of tangent there, of x naught, which we've figured out is pi over 4. So I need to find the derivative of f. The derivative of tangent, hopefully you remember, is secant squared of x. And we're going to evaluate secant squared of pi over 4. Now, if you're a little rusty on the unit circle, you can think of secant in terms of cosine. Recall that cosine of pi over 4 is the square root of 2 over 2. Secant, therefore, of pi over 4 is the reciprocal 2 over the square root of 2. And when we rationalize that, we end up with square root of 2. So we have 1 over secant of pi over 4, which is square root of 2, squared, and we get our final answer of 1/2. Thus, we can say the slope of inverse tangent of x, let me write it in function notation, f inverse of x equal to inverse tangent of x at the point 1 pi over 4 is 1/2. The thing you need to observe, what's the big picture here? We have found the slope of an inverse function without ever differentiating that inverse function. Let's try another example. If the slope of y equals f of x at ordered pair 2, 3 is 1/5, find the derivative of the inverse at 3. Now, it helps to sort of sort out x naught and y naught, f and f inverse, so I'm just going to write some information over here. Notice this point belongs to the function f this time. So we could observe f of 2 equals 3. Similarly, we could reverse that and say f inverse of 3 equals 2. Thus, x naught is 2, y naught is 3. Let's write our formula. That's the guideline that we're going to follow. F inverse prime of y naught is equal to 1 over f prime of x naught. Make sure you distinctly read inverse and prime notation differently, right? Now, we have established that y naught is 3 and x naught is 2. On the left of our equation, we have what we are seeking to find, and on the right side of our equation, it looks like we need to take the derivative of f at 2. We don't have the rule for f, we simply have the slope of f. So remember, f prime of 2, this is code for the slope of f of x at 2, which we know is 1/5. So we can replace f prime of 2 with 1/5. 1 divided by 1/5 is 5. Thus, we can say f inverse prime of 3 is equal to 5. So it really helps to patiently identify x naught and y naught and clearly distinguish between a derivative and an inverse. That theorem is going to take a little bit of practice. Now, if you really want to challenge, let's look at this next part. Note, part 1 of the fundamental theorem of calculus, that's a pretty important theorem, it's the central theorem for all of calculus. Part 1 states that if f of x is continuous on the closed interval from a to b, then big F of x equal to the integral from a to b f of t dt for a less than or equal to x less than or equal to b is continuous on the closed interval from a to b and differentiable on the open interval from a to b. So basically this is saying that the antiderivative is continuous and differentiable. In addition, big F prime of x is equal to the derivative with respect to x of the integral from a to t of f of t dt, which is a function of x. So this is a little bit complicated, but what I want you to see here is the overall pattern. Notice I've paired up two inverse functions, a derivative and an integral. Remember, big F represents the antiderivative of little f. So the antiderivative is big F, and I'm trying to find the derivative. So I am differentiating an antiderivative. That means I'm not getting anywhere. It's like adding and subtracting the same number or multiplying and dividing by the same number. We're applying two inverse operations in a row. So we end up with the original function, right? But there is a bit of a change in variables here. After we evaluate and differentiate with respect to x, we end up with a function of x. So what's the bottom line if you're confused? The derivative of an integral is simply the integrand, right? Let's see if we can apply this on example 9. Verify that f of x equal to the integral from -2 to x of t cubed minus 8 dt has an inverse. Now pause right here for a minute. Notice that we have the variable t in the integrand. That's kind of a dummy variable or a placeholder variable. After I integrate and evaluate upper limit minus lower limit, observe I will end up eventually with a function of x, right? So we're dealing with a function of x. Once I verify that this has an inverse, then I'm going to find the derivative of that inverse at 0. So let's observe that t cubed minus 8, so number 1, note that t cubed minus 8, think of the cubic function that's been shifted down the y-axis by 8 units. Notice that t cubed minus 8 is always increasing, This is called monotonic. We will define that officially later on. If it's always increasing, then it is 1-to-1. Thus, it is 1-to-1 and invertible. So we have verified that it has an inverse. Now another layer we need to add here, the integral is the area function. If the integrand is increasing, then the area function is increasing. Let me be specific here. The area function is also increasing 1-to-1 and invertible. So we know that it has an inverse. Number 2, let's talk about differentiating this function. F prime of x, so I'm looking at my function f of x here, and I'm going to differentiate with respect to x. This is going to be the derivative with respect to x of the integral from -2 to x of t cubed minus 8 dt, which by the fundamental theorem of calculus is our integrand, right? I'm differentiating an integral, applying two inverse functions successively. So I'm going to end up with the original function, which is x cubed minus 8. And we can say that's by the fundamental theorem of calculus. So now that we have the derivative of our original function, we can start working on the derivative of the inverse function. But let's make some observations first. We could say f inverse prime of y naught, which is equal to 0, has some corresponding x naught, which at this point we don't know, right? So y naught is equal to 0. We need to find the corresponding x naught. Well, if we make that statement, then we can reverse it and then say f of 0 equals x naught. Let me remove that prime over there for a minute, okay? Whoops, sorry guys, let me backtrack. Did you catch my mistake? I'm supposed to switch those. F of x naught equals 0. So if the inverse function evaluated at 0 gives me some output x naught, then I'm going to reverse that. F of x naught equals 0. Now let's evaluate f of x naught according to the definition of the function up here. So f of x naught is equal to the integral from -2, I'm plugging in my argument here, x naught, of t cubed minus 8 dt. And we know that this is equal to 0. Now look closely. If the integral from -2 to some x value yields 0, if the area function is 0, then we can observe that must mean that this upper limit is also -2. Therefore, x naught equals -2. So once we have found that mystery number, then we can say f inverse prime, f inverse prime of y naught is equal to 1 over f prime of x naught, which we figured out is -2. Now don't forget, back up here, we said the derivative of f is x cubed minus 8. So we can, let me get some room over here. We can say thus, f inverse prime of 0 is equal to 1 over the derivative, which is x cubed minus 8, evaluated at -2. Our calculations give us 1 over -8 minus 8, or -1 over 16. So that last problem is a little more challenging. The bottom line, what you really need to focus on, what you really need to know from this section is this formula, the corollary, which stems from this theorem. understand the relationship between the derivative of a function and the derivative of the inverse function. Now, as we move forward in Chapter 7, we're actually going to look at how do you find the derivative of inverse tangent and other transcendental functions as well. So you'll be able to differentiate directly. All right, you have completed the lecture videos for Section 7.1, and you are ready to proceed to your Section 7.1 homework. Hope it goes well for you.